So when you're tasked with doing this problem, there are multiple ways you could set yourself up to do this. This can be done using a motion equation if you figure out the acceleration. You can figure out the acceleration using Newton's laws. So there are a variety of ways to do it. You can do that. That would be one of them. You could do this as a work energy problem, as we've been talking about, but there's actually more than one way to do it as a work energy problem as well. You're going to have to settle on one that you feel suits you the best. The way I'm going to settle on it is what I'm about to show you. But like I said, you don't have to do it this way. At this point, you have a variety of methods at your disposal. I'm trying to encourage us to use energy, though. And the first thing I want to point out is the car has 9 joules of energy. Because we can calculate kinetic energy as 1/2 mv squared. So I'm hoping that that wasn't preventing you from getting any further in the problem. 9 joules. Now, how much work is necessary to stop the car? -9 joules. Right? To stop the car, I need to change its kinetic energy from 9 joules to 0. So technically, the amount of work necessary would have to be equal to -9 joules. We are accounting for the energy here. And the little car has to lose energy in order to come to rest. And we say lose energy, it's losing kinetic energy. I'm going to bring that to 0, which brings me to the fact that when it gets onto the ramp, there is going to be work done by the gravitational force. Is that a hiccup?
Yes.
Fantastic. Have I mentioned how much I love the hiccups? Not for me to get done, but to laugh at other people who do. Are you one of the people who gets hiccups like 3 times in a day?
No, I don't think so.
There are people who, I think it's genetic. When they get them once, they will get them 2 more times over the course of that day. My oldest daughter is one of those people, and she has amazingly loud hiccups. I make fun of her relentlessly when she has the hiccups. Those are good days. So let's talk about the fact that there are 2 possible forces that can do work on the car, right? Because there's only 2 forces that are acting on the car. There's the normal force on the car from the ramp. I don't think this force can actually do work on the car, though. Is there a component of the normal force in the direction of the displacement? No, there isn't. The normal force is 90 degrees from the displacement because the displacement is going to be in this direction. It goes up the ramp. So when we're looking at what's happening to the car, right there, if this is the direction of the displacement and this is the direction of the normal force, that's going to be 90 degrees. On the other hand, there is a gravitational force of 20 newtons that's going to act on the car. And there is a component of the 20 newtons in the direction of motion. Now, how you handle this 20 newtons is up to you. I know how I'm going to handle it. I'm going to say that the work done by the 20 newtons is a constant, and because it's a constant, I can use this relationship to figure out how much work is done. This is Physics C, so I have to remind you that if you're coming here from AP Physics 1, there's an extra step in there. You do need to evaluate whether your force is a constant or not. Because if it's not constant, you're stuck with calculus, which is a realistic thing to expect on your exam. If there's a straight work problem on the exam, they're not going to give you a constant force. They are going to give you a force that changes with position. So you need to be prepared for that. Ask that question. Don't become complacent. This is where AP 1 students have a disadvantage over students who are actually never had physics before, because they're being forced to consider the fact that there's a different way to calculate work, and they're having to make the decision that you never made last year. So keep in mind that there's just as many possibilities that you would have to do this to calculate the work as this. Don't be complacent. Our force is constant, though. This is gravity. Gravity acts on it in a constant manner, meaning it's acting in the same direction and at the same size. You have to evaluate both of those. So since the force is always downwards and the ramp is always of uniform length and direction, I can skip this one and focus on the top one. We haven't had an example in class yet where we can really use the integral. We will, just not right now. 3 buckets here. So I'm going to use the weight, 20 newtons. You might use a component of the weight, mg sine theta or something. But I'm just going to use the weight. I have it. It's 20 newtons. I don't know how far up the ramp it goes, but I know that this angle right there has got to be the angle between the displacement and the force. Now, I need to figure out what that angle is. I don't know that one. I know this one, though. Right? Based on the triangle, that one's got to be 50 degrees. That suggests that this one is 130 degrees. I'm going to use that for the work done by gravity as the car goes up the ramp. Any question about that? Because that has to equal -9 joules. This is how much work I have to do in order to stop the car. I need to take away 9 joules of its kinetic energy. Pretty sure you're going to get about 70 centimeters. Any question about this? This is not quite at tomorrow's level. We're going to add a few things today to put it at tomorrow's level. Of course, you've been doing your homework, so I'm sure that your homework has assisted you in doing this. But this is a good starter point. If you could do this, I'd say you're looking at a solid B tomorrow. You might have to do a little more than this tomorrow to get that A. I will stop right now, though. We're going to talk today about the elastic force a little bit, and I'm going to do so by talking about what's known as an ideal spring. And if I was a better teacher, I would have gotten out the prop that I had prepared for this, but I'll be honest, I've just been very inundated with stuff for Busch Gardens, so I have not had a chance to prepare what I wanted to talk to you about. But I do think that most of you have a concept of what a spring is. So for just a few moments, I kind of want to work off that concept and take this spring that I have sitting here and hang it. And also place one of them on the ground. Okay, so 2 different springs. Not a huge, I think, surprise that if I have something, a box, and I go to hang it on the spring and let go, would you agree that the spring will stretch? So if I place the box on the spring, I'd expect the spring to stretch until it comes to this kind of equilibrium position. At the same time, if I took the same box and put it on top of a spring, would you also expect that the spring would compress? Because the box is on top of it. Gravity pulls it down and the spring bunches up because the box presses down on the spring until it comes to some equilibrium position. Now, in either case, the spring is applying a force to the object. I think we can probably identify that here it's like a tension, right? It's pulling on the object, and here it's like a normal force because it's pulling up on an object. That's what springs do. They can apply tension. They can apply a normal force. They can be used in either case. There are things about springs that are important but don't look like they're important. For example, in both cases, the spring has something it's affixed to, something that holds one end of the spring in place so it can't move. This is what allows the spring to stretch or compress. What makes something an ideal spring, I'm going to be very careful about the way I say this so that I'm using my language appropriately. An ideal spring is one that stretches proportional to the applied force. That's what makes it an ideal spring. It stretches proportional to the applied force. And it's quite stupid simple. If I double how much force I apply to the spring, I expect it to stretch twice as far. Or if I double how much force I place on top of the spring, I expect it to compress twice as far. Does that make sense? So I make this box bigger, then the spring will stretch more. Is that okay? Now, what this means effectively is that the applied force on a spring is proportional to how far it stretches. So X represents how far the spring is stretched or compressed, and F represents the amount of force you get from your spring. Now, this is known as Hooke's law, and it applies to ideal springs. Now, before I go into this too far, I need to at least give you some nomenclature. Hooke's law is from the vantage point of the spring. This is the force you would get from the spring. That's important because that means it's negative. It's from the vantage point of the spring, meaning if I push on the spring to the left, the spring tries to push back to the right. If I pull down on the spring tries to pull up. That's this case. If I push down on the spring tries to push up. So the spring is always trying to apply a force that returns it to its original position. I'm not going to say that a dozen times, I'm going to say it twice, but I can't emphasize how important that statement is. A spring tries to apply a force to return it to its original position. Now, we don't study Hooke's law and springs because there's so many springs in the world and we can't wait to find one. We study Hooke's law and springs because there are a lot of things that act like they have a spring in them. An inflated ball does this. If you push on an inflated ball, there is a force that's developed to try and push it back to its original shape. That's why they bounce. They are elastic. All of these things deal with elasticity. So things that are elastic can be deformed and they will return back to their original shape. So anything that has elastic principles obeys Hooke's law to a certain degree. So we study all sorts of stuff. Anybody who shot bow and arrow, you have pulled back on the bow, that stretches the elasticity of the bow. The bow attempts to return to its original shape. It applies a force to the arrow. We study these things for a number of reasons, but one of the most important one is that the Hooke's law force is a conservative force, which, although I've not developed this word too much, conservative forces store energy, and that makes them useful. Almost every toy you played with as a youngster probably used a spring to store energy. They're cheap, they're easy, and they're compact. So there are lots of places where Hooke's law appears, but Hooke's law has a bit of a problem. First, it's a force that depends on displacement. We've never seen a force like this before. Every other force we've dealt with has been a constant. But this is a force where the more you push against the spring, the more force it's going to take to continue. So if you just start pushing on a spring, it takes a little bit of force, but the force that's required to continue to push on the spring grows as you push on it. So this is your first experience with a non-uniform force, a force that changes over a displacement. Of course, I'm bringing it up because we're talking about work, which is force related to displacement. So we now have our first example of an object where the force required to change the object will depend on how much you move against the object. So doing work to compress a spring will require us to integrate to find out how much energy it takes to compress a spring. Now, before I go into this too much more than this, there are no real ideal springs in nature. There are real springs in nature. There's rubber bands. There's the inflated ball. There's toys that pop up or pop out. There's all sorts of things that have elastic properties. None of them are perfectly ideal. We study the ideal case because the ideal case is relatively easy, and lots of things have parts where they are ideal. But you can't pull on a spring indefinitely. You'll bend it. You can't push on a spring indefinitely. Eventually, all the coils will touch and they'll stop moving. Springs have limits to how far they can be deformed before they rupture, break, or deform permanently. So real springs don't allow for them to be done just however. Most real springs have elastic limits before they change. So we will stay in the area of the ideal because a lot of things have an area where they work like they are ideal springs. But they all have limits. Now, the first thing I want to do with this is I want to point out that I'm not as interested right now in the force from a spring, although that will become a critical factor later in the year. Right now, I'm interested in the work done in compressing a spring. So we're going to do a little bit of quick mathematics here to kind of exaggerate or exemplify it. And I need to do this two different ways. The first way you're not going to get, and it's because you're not prepared for it. But Hooke's law is linear. And people, students especially, hate when you bring in multiple different forms of mathematics in the same conversation. But Hooke's law fits the bill for y equals mx plus b, doesn't it? If I plot force on the y-axis and x on the horizontal axis, this should be a straight line with a y-intercept of 0. So by putting that here, I'm pointing out that if you're presented with a graph of force versus position and it's a straight line, good chance that force is coming from a spring. But also, something else you're supposed to kind of remember is that if you're presented with a graph like this, you're supposed to test graphs for the meaning of the slope and the area. Now, not every force versus position graph is going to have a slope that's the spring constant. But every force versus position graph will have an area that represents work. The area under every force versus position graph will be the work done by that force. So you could be presented with a problem like this, where you are given a graph that perhaps looks like this. I'm making it look more complicated than I need to, but you don't know what kind of force. This force is just not constant. What would you do with that? Well, you would find the area under the curve, and that would be the work done. I would probably break that up into lots of little pieces, all sorts of triangles and rectangles, and add up all the different areas. So I've given you a practice like this in your homework. If you haven't done it yet, please get to a question like this. I want you to have tried it. The area under this curve is the work done by that applied force. Now, we have the added benefit of having done a little bit of calculus, which allows us to talk about the work done by a force that is not constant. That's what this is about. So I want to do the calculus here. It's okay. I don't lock my door though, so you're clear to close it. Figure that. If it wasn't a teacher, I think stand up. I have some jokes. They're funny sometimes. That one's not that funny. It was at the expense of one of you. All of my jokes were at the expense of one or two of you. That's what makes them funny. Because we're laughing at you, not with you. Good times. So, I want to walk through this process real quick, but I don't want to make this too difficult. And I also don't want to make it too crazy with negative signs and positive signs. That part's going to work itself out. It's not that hard. But I do want us to realize that in doing this, we are trying to calculate how much energy is stored in the spring. So our job in doing this is to take an expression for force that's in terms of a displacement. Ignore the negative sign. I could leave it there. It's just going to make our answer negative. So can we just ignore it for a bit? If you're desperate, I'll put it in there. I'm going to put the little squiggly here because it means to add up. But I also have to look at this function and figure out which one of these variables is about the change in position. And are they using the same variable that my generic equation is using to discuss change in position? This one just happens to, but doesn't have to be that way. If I hung the spring, vertically, I might be thinking that it's the y direction. So just be aware that this isn't like it has to be x. It has to be whatever the direction of the change in position is. That's what that's about. So force it to match what you have. I have something that's with x though. So that makes this pretty easy. I can just put dx here. Now for you guys who are new to this, don't read too much into this. First, you're not going to be tested on calculus first semester. Second semester though, the gloves are off and I'm going to put in calculus. But second, we've already done this problem. We have taken the antiderivative of an exponent. And that's all this is, with a little extra flair. The little sign there is a place for me to hang how far I'm compressing the spring. In this case, I'm starting with an uncompressed spring, 0, and I'm going to have a final position I compress it to, x final. I'm just writing a little f there so I know that it's different than this generic x I have inside. That's it. Now your problem might tell you you're going from 5 centimeters to 20 centimeters. You would put 5 to 20 in there. But we don't have that. We're just trying to figure out how much work is done compressing the spring. Are we okay to move on with that? Doing this, doing an integral, is 2 steps. One step you've already done, the second step we're doing now. The first step is the antiderivative, which is the entire scope of calculus. You guys who are in calculus know that you spend most all of your time figuring out the antiderivative. Because the second step is just putting in your limits of integration. That's stupid easy, and everybody can do that. It's just algebra. So again, the real hard part in calculus is to figure out the antiderivative, because they're not going to give you just something stupid easy like this. You spend all of your time learning how to do an antiderivative of something that's complex. Luckily, in this class, none of ours are very complex. In fact, if you can get by with the polynomial rule, you've got 40% of what's going to happen in this class. And the polynomial rule is pretty easy. Add 1 to the exponent and divide by the new exponent. Move on to the next polynomial. It's that straightforward. You do have to know, though, what's a constant and what's your variable. K is my constant. I'm reminding you of that because that's like saying 2x and asking for the antiderivative with respect to x. K is just a number. I could even pull it out front of the integral symbol. I'm allowed to. The integral symbol is like a parenthesis. So 2 steps here. Step 1, antiderivative. So I bring the k down because it's a constant. This is x to the 1 power. So my antiderivative will be x to the 1 plus 1, that's 2, divide by my new exponent, that's 1/2. Now that I've done that, I'm done with the symbology that tells me to do that. So I dispense with the little squiggly s and the dx. But I put a bracket here because I'm supposed to hang my limits here to remind me that I have a second step. Now, the second step is stupid easy. The second step just means to put in my limits, which means put this in for the variable first, and then subtract putting this in for the variable. That's all it means to put in your limits. So I will put in the first limit, 1/2 kx final squared. Just reorganizing it a little bit. And I'll put in the next limit, 1/2 k times 0 squared. Did I lose anybody? Not terrible? Because if you can't follow this line of reasoning, that's okay right now. All I will really care about is what I'm going to say here right this moment. That when you do work on a spring, the energy stored in the spring is equal to 1/2 kx squared, where this is how far it was compressed. This assumes the spring was in its relaxed state before it was compressed. Okay, does that answer your question? Okay. So we assume that we started with no energy in the spring, and this is how much energy is in the spring. It's really pretty easy once you've done this a little bit, but please understand that if you want to compress a spring, this will tell you how much energy it's going to take to do so. Or if you want to pull out a spring, that'll tell you how much energy it's going to take to do so. You have to know stuff, though. You have to know things like the spring constant. K is the spring constant. It's how powerful the spring is. Generally, you would expect that to be a big number, not a small number. It's in newtons per meter. That's the unit of the spring constant. Because it's based on Hooke's law. So it's in newtons per meter. I want you to think about what that means. That means it's how many newtons you get for every meter you compress a spring. How many of you have seen a spring in real life? Like a slinky or something like that. All right. Pulling it a meter is a long way, wouldn't you agree? Generally, like if you sit in your car, which is on 4 springs, does your car sink many meters into the ground? No. I'd argue that your 600 to 900 newtons of weight sitting in the car doesn't cause the car to change very much, does it? That's probably likely, just a couple of centimeters. So when I sit in a car, I am a lot. I am like 850 newtons. I'm a big guy. When I sit in my Jeep goes down about 2 centimeters. That suggests spring constant's pretty high. It goes down 0.02 meters under the pressure of 800 newtons. So can you get why spring constants are big numbers? So if you work something out and at the end of your problem, your spring constant is 0.4, you're wrong. It will not be 0.4. It'll be 1,000, 10,000. Okay? Toys will use spring constants between 500 and 1,000 just to shoot a little ping pong ball. So don't expect that you're going to have a spring constant that's a small number. X, on the other hand, pretty small number. We don't press springs in or out very far. Even a bow, the max, maybe a meter. So when you consider the displacement of a spring, you're going to expect that to be pretty small. You know, a couple of meters would be a long way to compress a spring. So go back to the problem we did at the very beginning of class, if you don't mind. I said that we had a ramp, and you guys were successful in finding out how far up the ramp the little car went. What if instead we're going to back the little car up against a spring and shoot the car towards the ramp? So we've pulled the car back a distance x against the spring. And the spring has a spring constant of 200 newtons per meter. How far would I have to pull the spring back in order for the car to go to that 0.7 meters up the ramp? Now, I'm going to run out of time here, and I don't want to. So I want you to pay attention very closely. You do not have to redo the entire problem from before. What I want you to see is something different. I believe that most of you recognize that the car had a certain amount of kinetic energy, right? This was taken away by the work done by friction. Not friction, gravity. Right? That's how it got to be up here. But now I'm talking about a problem where I have energy in the spring. and that spring is going to do work on the car. Now, how much work does the spring have to do on the car? 9 joules, right? The car had 9 joules. I don't have to worry about this part of the problem. I know that if I can give the car 9 joules, it's going to go 0.7 meters up the ramp. So I don't really have to make a comparison with how far up the ramp the car is going to go. I can make my comparison with how fast or how much kinetic energy the car had. And I can state that, well, this has to be the energy that is in the spring. I am accounting for the energy. I'm trying to trace where the energy was going. So right now, the energy is between the car and the spring. If I release the car, the spring is going to give that energy to the car. How much? 9 joules. So if I want to make sure the car gets the 9 joules, I better make sure I pull the car back far enough against the spring for it to get the right amount of energy to shoot up the ramp. Now, you note I don't really care what this answer is. It's demonstrative. But you probably got a couple of centimeters. Yes, ma'am? So here's the thing, and I'm trying to be, and I'm not trying to be evasive, but I know I'm limited on time. I'm tracing the energy. I know, you're right, that the hill's going to take away these 9 joules. But I need the spring to give the car 9 joules. The truth is, you're right, there's a lot of positives and negatives that I am just glancing right over. And I'm doing it on purpose, because I'm limited on my time, but the spring is going to lose 9 joules. Right now it has 9 joules. It's going to lose those 9 joules. So negative 9 joules of work will be done on the spring to take away that energy. Positive 9 joules of work is going to be done on the car to give the car the 9 joules. And then eventually the ramp is going to do negative 9 joules on the car to take away that energy again. But it's still all about the 9 joules here, right? So instead of worrying about those negative signs right now, I'm saying that the amount of energy that has to be in that spring needs to be equivalent to 9 joules. Does that make sense?